Good morning and welcome to NYU. Welcome to the Seminar Series, Circuits, THz and Beyond. I'm Ted Rappaport, the host of this seminar series, and on behalf of the NYU Wireless Industrial Affiliate sponsors of our Wireless Center here at NYU, it's my pleasure to welcome you to the third seminar in the continuing series. I'm very delighted to introduce to you today Professor Hossein Hashemi. Professor Hashemi leads research in optics and RF at USC and is a world leader in doing amazing things at millimeter wave and now moving all the way up to optical frequencies. We're in for a treat and delighted to have you with us. Professor Hashemi, the floor is yours. Thank you for coming. Let's give him a big NYU Wireless welcome.
Good morning. Thank you for the invitation and for the lovely introduction. A disclaimer, my talk is very long potentially, but I'll try to fit it into 1 hour. That's the first disclaimer. The second disclaimer is that I was told that the audience is pretty broad across engineering and physics. The good news is that the first half of the talk has a tutorial nature, so as long as you know the very basics of freshman level math or physics, you should be good for the first half of the talk. And the second half, I'll try to lead into a little bit more researchy topics. And I don't know whether it's okay for the live stream or not, but as far as I'm concerned, feel free to interrupt me with questions in the middle, and I'll just be glad to answer. As it's true with all of the faculty talks, the work is actually done by a collective group of students and postdocs. Today's talk is only focused on one research trust in my group, which is Phased Arrays, and these are the people who have been involved with it over the years and some of the funding sources that have provided us money for this particular set of efforts. I will start with introducing you to the concept of phased arrays. And I don't want to be preaching to the choir because I know that the NYU Wireless is the world's leader in propagation properties of systems. But it's probably fitting to start with a basic model of a wireless system where you have a transmitter on the left and a receiver on the right. And from the basic wave propagation, we know that the signal that propagates from the left to right over a distance is going to experience a delay. Right? So you get the same copy of the receiver, but with the delay and perhaps some sort of an attenuation in a real environment. So if I send a signal to you, it's going to take some time to get it to you. Now, as it turns out in wireless systems, oftentimes we're interested with systems that have the following form, which is that you have a signal that is multiplied by a carrier signal. This carrier, e to the j omega RFT, it's basically a sinusoid. So I place my information on a sinusoid, and I try to transmit it from one place to another place. Now, after some really basic algebraic manipulation, it will turn out that what happens when the signal reaches the receiver, the message that you have, this S of t, is delayed, but also your signal experiences a phase shift. See this term, e to the minus j 2 pi d by lambda? That's the phase shift. And lambda is the wavelength of the signal that you're propagating. So for instance, if the signal is at 1 gigahertz, that would be about 30 centimeters. If you're dealing with optical frequencies, that's a micron. So signal from here to here, I get a delay and I get a phase shift. Now, a very important property in physical systems is interference. So what happens if I have two of these signals? So now if I have two signals and they travel different distances, both of them reach here, but with different phase shifts. This is the phase shift of the first one, which is proportional to the distance from the first antenna to the receiver, and phase shift for the second signal, which is proportional for the distance of the second antenna to the receiver. So these two will interfere. Depending on the distances, sometimes they will interfere constructively, and sometimes they will interfere destructively. So you can plot that. So here I am plotting you the magnitude of the interference signal, or the signal that is received, versus distance. And as you can see, sometimes the signals add up. So 1 plus 1, it's 2 because I had two antennas. Sometimes they will completely subtract and you get 0. And because it's a periodic system, it will just repeat itself. All right, so this is the basic interference patterns that all of you in engineering physics are familiar with. All right, What happens if I have more than 2 antennas? In engineering and physics, we're very good with generalizations, so you can generalize this. You're going to have a summation of all of these phases. So depending on the relative distances, here sometimes you get addition of signals and sometimes you get subtraction of signals, multiple interferences. One special case is when the distance between these antennas is fixed. Let's call it a capital D. So there is a uniform placement of these antennas, and the receiving system is far away from the transmitting antennas. This would result in having your wave fronts that are usually spherical to be approximated with plane waves as they reach the other side. And therefore, the difference in the timing between these two wave fronts is going to be constant and proportional to the angle of incidence. The quick way to think about it is that imagine that your receiver is exactly at a center. If it's exactly at a center, the signal from all the transmitters to the center are going to be approximately the same if the distance is long enough. Now, if your receiver now is at the bottom, you can see that the bottom antennas would see the receiver first, and then the top antennas would see the receiver later. This would create a phase shift. You go to the math and you come up with some expression. This is called an expression for a uniform linear array, which is, again, an interference pattern, but for a lot of antennas. And you can plot that. You can plot that depending on the number of antennas that you have in the system. So this is an interference pattern when you have 2 antennas. Now, in the y-axis, you're looking at the strength of the signal, and in the x-axis, you're looking at the angle in which your receiver and transmitter are aligned. So 0 degrees means that your receiver is exactly at the center. 90 degrees means that it's completely on the side. So you can see that for 2 antennas, for all of the cases, whether you have 2 antennas, 4 antennas, or many more antennas, the peak always happens at the 0 degrees. If you have 2 antennas, the peak is 2. If you have 4, the peak is 4. 16, the peak is 15, and so on. But you also see another interesting property. That is, this shape becomes narrower and narrower as you have more number of antennas. In electromagnetics, we call that as narrowing of the beam. So it's as if you're becoming a more selective and selective system. In here, for instance, if you have 256 antennas, if you move a little bit away from the 0 degrees, you're not going to receive any signal. It's as if you don't see anything. Whereas if you're at the center, you receive everything. It seems that you're creating a directional communication system. It's like a laser pointer. It's very, very directional if you use a large number of antennas, compared to the case that I have only 2 antennas. All right, this is a very interesting property, and we're going to use it. Now, more interestingly, and also I'm showing the same plots as a function of the distance between 2 antennas. As it turns out, and it can be proved, that if your antennas are half a wavelength apart, that's your optimum point in the sense that you are going to get only one peak in this waveform. Whereas if your distance is larger, so I'm showing it for distance between 2 lambda or 4 lambda, you see there are multiple peaks. So here the signals add up at 0. They also add up at 90 degrees. In here, they add up at 0, 30, and 90. In here, there are many more peaks, which means that my point was to have a communication directional only with you, but now it's as if I'm listening to the 2 sides too. So I'm listening to 3 sides at the same time. And that's usually not desirable because these 3 signals that come at the same time, they interfere. I get confused who's saying what. I want to keep a directional communication. All right. So if that array is a good idea, why don't we play with it a little bit more? Specifically, instead of driving all of these antennas with the same signal, let's try having a complex weight on each antenna. Let's create a phase shift and an amplitude for each of these antennas. As it turns out, again, these things are going to interfere, but with a different phase shift that is not only a function of these distances, but also a function of the phase shift for individual paths. And once again, you can plot this, and you see something very interesting. This is the case where you had all of your antennas connected without these phase shifters. So your peak happens at 0 degrees. As it turns out that if you adjust the phase shift just about right, suddenly your peak moves to a different location. So your peak moves to minus 30 degrees, or to minus 60 degrees, or all the way to 90 degrees. And this was all done by just playing with these phase shifters, which are electronic components. In other words, if you have such a system, it's emulating what I'm doing with my laser pointer. In my laser pointer, I shoot the wall, and then I move my hand around to point at different locations. In the systems that I'm showing you, also, this beam is pointing in different directions, but nothing is mechanically moving. All the adjustment is done by electronic control of these phase shifters. This is a very powerful concept that has been known for a while as referred to as beam forming or phased array. So if I want to summarize everything that I said so far, which was more of a tutorial, in general, if you have an array of antennas and each of these antenna elements is driven by an individual phase shifter and amplitude controller, both the near field and far field radiation patterns can be adjusted. You can play with them both. Typically, or ideally, you want the distance between the two antennas to be half a wavelength. So if it's 1 gigahertz, it will have to be 15 centimeters. If it's 30 gigahertz, it would have to be half a millimeter. Or 5 millimeters, I should say, half a centimeter. And although I showed everything when your array was in the transmitter and you had one receiver, the system is reciprocal. So whether you have a number of array elements in the transmitter or receiver, you would get the same result. Very good. Now, there are some other properties that are very interesting and useful in practical systems. The first property is this. As I said before, if you have a number of antennas and each of them sends you a signal, when you receive it, you have n times this, 1, 2 to n, so they all add up coherently, you get n times the signal, which means that the power would increase by n squared. Now, if you wanted to get n squared worth of power to begin with, you needed to have a larger amplifier that gives you all that big power. It turns out that having an amplifier that gives you a lot of power is very, very hard. These things are usually bulky, and they're very sensitive. They can easily break. Whereas, if you have a number of array elements, even if you want to create a kilowatt of power, all you need to do is to create 100 amplifiers, each of you giving you maybe some milliwatt worth of power. So the system is more robust, and it's a lot easier to make. This is referred to as spatial power combining in amplifiers. You're combining the power, but they all add up in space. In the receiver, the situation is also interesting. Imagine that you have a receiving array consisting of a number of antennas, phase shifters, and amplifiers, and there is a received signal and received noise. Each of these receiving paths is going to have its own noise, and in most practical cases, these noises are completely uncorrelated. They're independent noise sources. Because they're uncorrelated, when they add up, they just add up in power, whereas the signal adds up in power in n squared. In summary, your signal-to-noise ratio at the output, that is the measure of the quality of the signal, how much my signal is above noise, improves by the number of array elements. So the larger number of array elements you have, the larger the signal-to-noise ratio. So this is another trick. If you want to improve your reception, just have more receivers in parallel. Now, is this all new? Like most things, the answer is no. This is not new. So, in fact, how many of you know Carl Ferdinand Braun? How many of you know Marconi? Right? Everybody thinks that Marconi is an inventor of radio, right? Okay, so as it turns out that Marconi actually won the Nobel Prize in Physics with Carl Ferdinand Braun in 1909 together for their contributions to the development of wireless telegraphy. So you can make your own judgment who is the real inventor of radio. And if you look at all the Nobel laureates give a lecture, a Nobel lecture, and if you read Carl's Nobel lecture, he in fact shows you a picture of a phased array. So he shows 3 antennas, and then he says that if I construct the 3 antennas, I can form a beam in a particular direction. Of course, being in 1909, the antennas were pretty large, the frequencies were pretty low, but the concept was definitely shown way back then. Now, again, like most things in engineering, this concept flourished during the World War II. Phased arrays were essential in the bombers that we had because they wanted to see where to drop their bombs, and also for the radars that were trying to see where the airplanes are coming from. The idea is that you would just look at different angles and you would scan them electronically as opposed to having mechanically moving antennas that would sometimes not work if a mechanical system fails. In more modern times, if you look, phased arrays are ubiquitous in military systems. So this is the one you're all seeing. This is a military Navy ship. So you've seen these radars, and I'll tell you exactly what's inside of each one of them. So each face, this is one radar, this is another radar. Each face, this circle, has 3,424 of those antennas. It's a very, very large number of antennas working at 8 to 12 gigahertz, and it's meant to detect the missiles and objects that come from abroad, because naval ships are very expensive. You cannot afford to be hit. You need to know where things are coming from and do something about it. Now, on the other side, if you're a fighter, you need to be very precise in where to attack. So this is a nose of an airplane. You're familiar to seeing a cone shape in the cone of a fighter. If you remove that cone, this is what you'll see. You see a phased array, a very large number of elements, again, 1,000 elements meant to detect different targets and track them at different times. Now, on the ground, military uses something like this, which is these gigantic systems, Patriot, that they try to find where the missiles are coming from and do something about it. Fortunately, in the US, we never get a chance to use them, but some other countries need to use them on a daily basis. These things are used on a daily basis in Israel. You might have heard of the Iron Dome in the news. So we said that the missiles that were flown over to Israel were shot down in a system that was very, very similar to this. That was developed by Israel and US jointly. They would detect multiple missiles and shoot them down. If you go and look at the videos, they're actually kind of cool how they can see it. So these are real systems. What they all have in common is that they have a large number of antennas, thousands of elements, and they all are based on using discrete electronic components. They need to be flexible, they need to be fixed soon, and they all cost millions and millions of dollars. In fact, if you look at the cost of something like an airplane or a naval ship, oftentimes the electronics cost is a significant portion of the total cost. How about, so what happened then? How many of you know Gordon Moore? Moore's Law? Moore's Law, everybody knows Moore's Law. So this is the Moore's Law paper, cramming more components on integrated circuits. Gordon Moore, the co-founder of Intel, paper was published in 1965. So what this paper told us is that the number of transistors probably can double over time, and this gave us the Moore's Law. But few people actually cared to read the paper. If you read the paper, this is how the paper actually ends. So the paper ends by predicting that over time, integrated circuits can enable phased array radars completely on a single chip at microwave frequencies. This is 1965. So this is when we did have phased arrays used in the World War II military, but nobody envisioned that they can ever be this compact. But he predicted that. And fortunately, it happened. So some 40 years later, this was the first phased array chip. This had 8 elements, 1 to 8. This was demonstrated at Caltech. I was a PhD student back then. So it took some 40 years, but finally, in a single chip, you can have the entire functionality of a phased array. So Gordon Moore was kind of happy. I hope he was. And you can see that you can form beams. So these are the beams that I showed you, those MATLAB simulations. Now these are some measurement beams. You can point them in different directions. I'll show you the architecture later, how this thing works. So what happened since? There's been a lot of progress. If you read the community, the number of phased array chips that were realized in silicon or CMOS was 1, because this was only 1 in 2004. And if you Google search now, there are hundreds and thousands. So naturally, this is not an exhaustive list by any means. I'm just showing you some of the highlights. So shortly after this first demonstration, people started to realize things at even higher frequency. So from 24 gigahertz, went all the way up to 77 gigahertz. The reason 77 gigahertz was picked is that this is a frequency that is used for automotive radars. We'll get into that too. So then people realized transmitting chips, receiving chips, then the entire transceiver chips. And as it's true for most of the research, initially everything is done in universities. So Caltech, USC, UC San Diego. But then very shortly after, so within a span of 5-6 years, industry research labs started saying that, okay, maybe I can work on it too. So Intel and IBM started to also demonstrate systems at 60 gigahertz. 60 gigahertz happens to be a frequency that is gained a lot of interest for various reasons. And believe it or not, even in 2011, we had a company that was selling products based on these phased arrays. Unfortunately, this company with this name doesn't exist anymore because it was acquired. The particular product they had, you might have purchased it if you don't know, is that they would have wireless HT transmission between a TV and a set-top box. So usually, at least in my home, the way things have is that I have a receiver, and then I have a cable that connects my receiver to my TV. Now, a lot of people don't like that cable for various reasons because of aesthetics. So this was a company that would remove that cable and give you HDMI wirelessly. And if you look at over the past 5-6 years, people have gone even to higher frequencies. So this is in 2012, and 280 gigahertz, 338 gigahertz. So it's been a lot of higher frequency. And companies, on the other hand, have started going to a little bit lower frequencies at 28 gig, for instance, because that just happens to be a frequency of interest for the next generation of wireless standards. All right, so it seems that the community has gotten comfortable with making phased arrays in integrated circuits, and that's why I'm not going to talk a lot about that. Now, what are the applications? The first application that was envisioned was automotive radar. As it happens, unlike New York, in California, we drive a lot. Without a car, we cannot survive. And there are a lot of accidents, too, because people are watching their phones or putting up makeup as they drive. So it's always good to find ways to make your cars safer. And one way to do that is to give eyes a way to see around them. And one way to do that is to use cameras. But cameras don't work at night, and you can be easily blocked. So another way is to use radar. So this is a conceptual scheme of a car where you have radar looking at different parts around the car to help the driver navigate more safely, and maybe in the future even the car can drive itself. This was a concept, I think it's a very old picture, probably 10, 15 years old, but now there are products in the market by various companies. These are just two of the companies. I'm sure there are many, many more that produce chips that can be used for phased array, for electronic beam steering of these radar beams at the frequency band that is allocated, 70 and 80 gigahertz. Again, just as a disclaimer, I should have said it early on, I am not affiliated with any of the companies whose products I'm showing right now, so this is just my Google search giving me these names. That's my disclaimer here. Now, on the wireless communication, do we care? I gave you one application where there was a wireless HDMI, but as it turns out, the next generation of wireless systems, widely known as the 5G, you might have heard it in the public news and in NYU Wireless, of course. It's supposed to be working at millimeter wave frequencies, and part of the advantage is that now you can have these beam forming. So if I want to have a communication in this group, instead of having an access node that sends the information everywhere, perhaps I can selectively send my information only to the intended user. And therefore, perhaps I can increase the capacity. In fact, I know that most of the implementation of the wireless networking at millimeter waves was actually envisioned at NYU, so it's very fitting to give this picture in here. I don't know if this is your picture or somebody else's picture. It could very well be yours. There are many products in the market already, although the standard, to my knowledge, is not ratified yet. But most of the companies don't have pretty pictures. The only one with a pretty picture was Qualcomm. That's why I'm showing this one. But again, I'm sure there are many more who have products. So what you're looking at is a CMOS chip that can have all these phased array functions, and in addition, it has all the antenna modules too. So the main difference between the commercial products and the military products are that they are all monolithic in a single chip. These are a few millimeters in dimension, and they have few elements, few being 10, 20, 30, 60. They are not thousands, at least not at the moment. All right, So with that said, given that the talk is 1.5, okay, so we have, all right. So I'm going to skip a lot of this stuff because I really want to get to the optics right now. These are some introduction, so let me skip them. You really don't need them. And I can lay actually these are the intro slides. I'll tell you what I'm skipping. I am skipping different ways to create phased array architectures. I can leave them to you for those who are interested. But I really want to get to the optics because that's where the fun is, especially for the physics and engineering audience here. All right. So why do I care about optics? Why did I have been educated and trained in doing radio frequency circuits for decades, and why did I suddenly decide that optics is a good thing to do? There were a few observations. So first of all, as it turns out, the backbone of internet is based on fiber optics. The reason all of you have wireless, have access to high speed, is because the information is transferred to optical fibers. And as it turns out that the fiber optic community has been using very expensive components for a very long time. These were discrete components that were hand aligned. But over time, things also went to the electronic route. We started miniaturizing them using silicon photonics technology. And the market is growing very fast. And because of that, the ecosystem of designing optical integrated circuits has evolved quite a bit compared to what it was even 5 years ago. There are a lot of emerging applications for optical systems, including 3D cameras. How many of you have iPhone 10? Okay, so a few of you. Face recognition, right? You look at it, it turns on, right? So the way it does it, do you know how it does it? No? So the way it does it, it has a lot of lasers. Those lasers would emit light to you. It's just lasers, you don't see them. It's not like this visible laser, it's a different wavelength. They hit your face, they reflect back, and then it would just reconstruct your face, and it will know whether it's you or somebody else. So suddenly, because of iPhone 10, before iPhone 10, this is actually a true story, maybe there were, I don't know, I'm making up numbers, some number of lasers that were sold every year. When iPhone came up with this concept, there were not enough lasers that were around to even make enough iPhones. So suddenly, basically, Apple had to invent lasers all over again in the manufacturing sense. So now the market of lasers is enormous, just that one application. LiDAR, how many of you have heard of LiDAR? All right, so LiDAR is basically equivalent of radar, except that it works with light. So I hit a light and an object comes back and I kind of decide where it is. It's made a lot of noise lately because of its potential application in self-driving cars, right? So I told you that radar is one application of self-driving cars, and LiDAR is another way, and camera is another way. So there are all these different sensors. Display projection holography, all of you now are familiar with your displays. A lot of people have been interested in creating 3D displays, three-dimensional displays, or displays that can give you a 3D view holography, hopefully in your iPhone. And there are some biomedical and sensing applications. So this was intriguing enough for me to decide to do optics. So what is the state of the art? This is a Waymo self-driving car. Waymo is a company that Google spun off. So Google worked on self-driving cars, and they decided to give it to Waymo. And the way Waymo sees around is that it has a lot of sensors. The most important sensor is the one on the top, this guy, which is very ugly. But this guy is a LiDAR, and the way it works is that it has a laser, and it sits on a movable platform. It rotates, it spins very, very fast, and as it spins, it tries to recreate the scene around it. The one that Waymo uses is a very expensive LiDAR. It's an $80,000 LiDAR by a company called Velodyne, which is an interesting story. It was a faculty member, a researcher, decided to start a company in Santa Barbara developing LiDAR for universities who were interested in purchasing the kind of thing that you want to do. And he was probably selling 10 per year, whatever, 100 per year. Suddenly, self-driving car came. He was the only one who had it. So he would still sell $80,000 worth of LiDAR to companies who were interested, but that would not be sustainable. You cannot put an $80,000 LiDAR on a car that is supposed to sell for only 10, 20 grand. So they came up with a cheaper model. So this is the cheapest model that I can think of is $4,000. It's a lot better, but it's still not cheap enough. And it has mechanical movement. So the question is, can I replicate this performance with semiconductors, nothing mechanically moving, and can I remove 2 zeros out of this? Because unless this is $40, $50, I cannot put it in the car and still sell the car at a reasonable cost, even if it's a self-driving car. Is it possible to do that? So how does it work? Oh, Here, perfect. So this is how the beam steering works, optical beam steering. You put a laser in a spinning platform and it spins. It gives you this $85,000 worth of equipment, all right? Can you do something else? So yes, as it turns out, about 20 years ago in Bell Labs, people invented or created this movable mirrors. So these were mirrors at a very tiny size. These are tens of micrometers, and they are in a single chip, and they could move by applying of some electrostatic charge. And they were used initially for routing fiber optical signals. And later, I believe that TI bought the technology or recreated it. They call it DLP, Digital Lightweight Display. I don't know whether that one, is that DLP? That might very well be DLP, the one that is projecting here. So it's used for projection. So mirrors really move fast, and they can project different lights into here. There's a commercial, so probably you can use the same thing. There are some other properties that you can use. For instance, you can use liquid crystal material. So these are the material whose index of refraction changes if you apply a signal. And so when a waveguide signal goes in, you change the index, and the light goes in different directions. This company, Vescent Actually Analog Devices, purchased this company a couple of years ago because they're interested in, they're actually right around here somewhere, maybe in Boston actually. They're interested in self-driving cars too, so they want to make this with their CMOS chips to do that. And then there are some other ways to create acousto-optical signals. So this is what exists right now, and they all work very good. But then, because I was working in a radio frequency phase array, I decided, okay, why not do the whole thing in optics? I just told you a minute ago that if I have a bunch of antennas, variable phase shifters, and amplifiers, I can move the beam electronically. I don't need to have any mechanical movement. I showed it that it works in RF. I had confidence because I was the first person to do it in RF. Why not do it in optics? Well, things are very, very hard. Because I told you that in a good scenario, this distance, d, has to be half a wavelength. In radio frequencies, things are easy. So even at 30 gigahertz, which is a very high frequency, 30 times higher than the frequency of your cell phone, the wavelength is 5 millimeter. 5 millimeter is a large spacing, believe it or not. In optics, wavelengths are about a micron. So these antennas have to be placed half a micron away. Now, that's not easy. That's very, very hard. Now, again, just because I'm very interested in the history of science, I tried to see if I'm the first person who ever thought of an optical phased array. And obviously, I was disappointed because things have been known before. In fact, this is even more fun. So laser was demonstrated in 1960, and then just a few years later, people started filing a lot of patents, and they said that, yes, optical phased array can exist. Now, they couldn't implement any of their cartoons, but they had the cartoons. And believe it or not, they even envisioned the applications. They said that you can use this device for display, and they can use it for optical radar. In fact, the term LiDAR didn't even exist. They envisioned the application as being an optical radar in 1963. Then, of course, technology evolved a couple of decades later, and then just recently, just since 2010, people have started saying that, oh, okay, maybe I can realize all these phased array functions in silicon. So I'm going to talk about that a little bit more. All right, so first of all, what is this silicon technology platform? Just for those of you who don't know anything about optics, I hope everything knows something about refraction, right? Light gets in the water, they get reflection, fine. So basic physics, you have two material with two different indexes of property. If N1 is bigger than N2, you get total internal reflection. Total light just does this. That's all you need to do. So this is going to be my optical waveguide, all right? That's all we need to do here. So how do I realize it in the chip? In an integrated circuit, the materials that I have accessible to me are silicon, silicon oxide, silicon nitride. And as it turns out, the refractive index of silicon and silicon nitride is bigger than silicon oxide at infrared. So just a box like this can act like a waveguide. A structure like this can act like a waveguide. A box like this can act like a waveguide. Those of you who are more familiar with optical stuff, these are the optical modes that they show that they're pretty well confined in all these three structures. And this is completely compatible with commercial foundry processes like you do with Intel or IBM or whoever else has a foundry process. Now, Once you have a waveguide, you can even bend the light. So this is a waveguide that just bends like this. And the bends can be pretty tight. This is a SEM of a structure we taped out, so you can see the light can be bent. And depending on the curvature, the loss is going to be more or less, if you bend it really tight, the light cannot really bend that fast, so the loss increases. And if not, the loss is pretty okay. Again, once you have a waveguide, you can have fancy structures or fancier. So for instance, you can have two waveguides next to each other. When light is traveling to this one, some of it can couple to the top one. So now you have a coupled waveguide, a structure like this. This shows you a field. So light comes from the top one, and over time, it couples to both of them. So now the light can come up with both cases. So this can be used, for instance, as a 50-50 power divider. Light goes in, comes out 50% at the top, 50% at the bottom, or any percent at the top, any percent at the bottom. So this is called coupler. All right. You can have even fancier structures. So a waveguide goes into what we call a multi-mode region. So a single mode propagates here. It creates multiple modes. These multiple modes can then add up or subtract destructively, and then again feed to single mode waveguides. Long story short, you can again have power combiners or power dividers in a very, very tiny form factor. This is just 2 microns by 3 microns. Very, very tiny.
Where are you fabricating these again? Repeat the question.
Silicon photonics. These are all in silicon technology. The particular foundries is about 2 slides from now. All right, now I need an antenna, right? So how do I send the light out? So the antenna is a simple grating structure, silicon waveguide. We know from basics of grating, once you hit a periodic boundary, the light is going to face a different refractive index, and then if you design it well, the light can just get out of the chip. This is a real structure that we have created. So a waveguide goes in, the gratings are in polysilicon, and you can see it's a very tiny geometry. It acts as an optical antenna. Now, we need a phase shifter. Now, this is a hard one. This is still a research. Basically, you need to have a waveguide. When the light goes in, it comes out with a different phase shift. Now, it's really, really hard. The only option you have is to change the index of silicon, and the index of silicon doesn't really want to change. It does change with temperature. It does change with free carrier concentration, and there are some different effects: Franz-Keldysh effect, quantum confined Sard effect, Kerr effect, Puckle's effect, and different effects can be used and have been used into creating different indexes and phase shifts. One of them is heating it up. So get a silicon waveguide, have heaters next to it. Now, it doesn't mean that I just put a hair dryer next to it. What I do is that I just have a piece of conductor and I pass current through it like a resistor. It heats up enough so that this heats up, and then that creates a phase shift. Cool idea. Or I can get my waveguide and put a PN diode around it, inject carriers into it, electrons or holes. That will also create an index change. So these two can be used, and other effects. I'll get to this a bit later. Now, this one partially responds to the previous question. So I showed you some optical components, but what is the platform that I'm using? This is a generic platform. It's called a silicon and insulator platform because you have silicon, then you have an insulator, which is silicon oxide, and then on a mechanical structure, which is silicon. These are the waveguides that I showed you on the left. This is that heater that I showed you, and this is a carrier injection. And of course, in the right, I have my transistors. So this is the backbone of electronics. So this whole picture shows you an ideal process that can give me both electronic functions and optical functions. So I can have an entire LiDAR on a chip because I can have my digital signal processor on the chip, and I can have my light phase shifters and optical antennas and things like that. How do I make it fabricated? Now that's a more interesting question. So if you're interested in R&D, there are quite a bit of places, unfortunately most of them in Europe, and color codes indicate different things. When you see yellow, that means that these foundries only give you silicon photonics, no transistors. So you don't have any electronics, you can only have photonics. And if you have this color, which is only IHB in Germany, they give you silicon photonics and electronics together. So you can go to any of these places and they will make something for you. The AIM Photonics is a new entity. It's a federal institute that is being created actually in your state. It's up and running, kind of. It's getting there. So hopefully soon enough, this will have even more capabilities than what it already has. Now, how about the production stuff? So the production stuff are, the main one is Global Foundries, again in the Northeast. They can give you processes that are only, that have electronics and photonics. There is a company in Southern California, Tower Jazz. The reason you don't see any entries here in the Luxera and TSMC is because they're all secret, so I don't know what they have. I know they have it, but I don't know what it is. And then there are companies in Singapore. So these are your production ones. If you want to manufacture things with volume, you probably have to go with one of these or the ones that are in the future. So a structure of a phased array, if you're dealing with one-dimensional phased array, which is that you have a linear array of antennas, the signal can go in, they split, go to amplitude adjuster and phase shifter to this antenna. Now you can see that in this particular case, the antennas can be very close because I can route them to large structures that are outside. So one-dimensional optical phased arrays with small distance is very easy. Two-dimensional is very hard because now the distance between two antennas, either in the vertical axis or in horizontal axis, is limited by how tiny I can make this entire structure. And this entire structure is incredibly hard to make it small. As a result, all of the demonstrations by research community, the good ones, are based on one-dimensional arrays. So 2D arrays is a hot research topic. Lots of money is being thrown at it. We don't know how to do it yet. Let me show you two examples fairly quickly. So the first example, we had a 2D array, so we attempted to do the hard stuff, knowing that we probably can't make these antennas too close, and they will not be very close. So the structure, light comes in, it couples into waveguides that go up, so any line that you see is a waveguide, and then it couples into unit cells that are variable attenuators, variable phase shifters, and optical antennas. The process we used is the Global Foundries 180 nanometer SOI CMOS process. This is a cross-section of the process you're looking at. This process is used for manufacturing radio frequency switches. It's not meant for optical performances. But we, at the time, this is many years ago, had no choice. We didn't have a process that would give us optics and electronics. So we took this process, we begged Global Foundries, back then IBM, to tell us the recipe of the process. They didn't, so we reverse engineered it. We placed a lot of structures and we tried to guess what the process properties were. I think we succeeded pretty well. And then we shared it with everybody, of course. And so we probably have a good understanding of this process. These are the measurement results of a single waveguide. So the loss is at 1.2 dB per millimeter. These are the couplers that I showed you. This is a multimode interferometer. So first we design individual components. And then we need a phase shifter. So I told you we have a waveguide with a resistor and we heat it up. So this is a measurement result. You can see phase shift changes from 0 to 360 degrees as you heat up, and the amplitude doesn't even change. Now, in reality, we meander the waveguide to consume less power, less real estate. I apologize. How do I get the variable attenuator? This is a fun game. So we split the light into two arms. In one arm, we put a phase shifter. We add up again. So depending on this phase shift, the light either adds or subtracts. So you get a variable attenuator. So you can see the attenuation changes as you change the heater power again. And this is how the structure looks like. So this is the entire system. It's an 8x8 array. Each unit cell consists of that antenna grading coupler, a variable phase shifter, a variable attenuator. This is a chip. We didn't have a good camera back then, so you don't see a lot. You see metal fills, a lot of it. This is a waveguide, for instance. This top of it is metal fill. You can't even see it. We measure a system in an optical setup, the usual setup, but let me show you the result. So we turn the system on, very excited to see a beam, we got garbage. Now, for those of you who've measured arrays, you know that what the reason for garbage is that you have a lot of mismatches between these elements. Nobody knows what the amplitude and phases are. The system must be calibrated. So then we calibrated the system, and man, it's hard at optical frequencies. You need a lot of patience. Once you do that, things start looking very good. Left simulation, right measurement. Near field, so all of the antennas are radiating, that's good. And you can see the far field pattern. You can see bright, and these are the grading lobes. Those of you in RF community, you lose this seeing this in 1D, so this is a 2D picture of grading lobes. How do I get rid of grading lobes? By playing with the amplitudes. So I can just focus without seeing the grading lobes. I play with the amplitudes and phases. How do I steer it? Like what I do with the RF, I adjust the phase shifter, so I steer the light from left to right or from bottom to top. But you can notice something. You can see a lot of dots. Do you know why? because my antennas are not spaced lambda by 2. They're spaced 15 lambda. There's a lot of grading lobes. That's the unfortunate part of the system. And it can create other interesting structures. In fact, I asked my students to write USC, but he was graduating. He wasn't interested, so he didn't do that. All right, so that was just 8 by 8, and we became more ambitious. We said, is it possible to do larger arrays, 1,000 elements? Why? Because with 1,000 elements, my beam becomes really narrow, 0.03 degrees. So not only I can use it for LiDAR, I can even scan your face and do some better. So I can detect objects that are hundreds of meters away with millimeter accuracy. I can do really, really well. All right, but then I need to space my antennas very, very close too. So the problem here we had is that, as I said before, if you have 1,000 elements, you need 1,000 phase shifters, 1,000 electronics. This system is going to be too big and too power hungry to be implemented in a single chip. So we came up with an architectural innovation here that was, instead of having a single array, we broke it into sub-arrays. So each sub-array has fewer antennas, and each sub-array is fed by its own independent phase shifters that are controlled together with the rest of the sub-arrays. So the system is hierarchical. And this is, therefore, the controls that you have are going to be fewer and only on the side. I'll skip this one. It's not needed. But let me tell you system evolution. So the system starts with what we call a sub-row. So 8 antennas, each of them with an independent phase shifter. Then we have 4 of these together, and we call it a unit row. So now 4 times 8 is 32, and each of these unit cells has its own phase shifter and amplitude adjuster. Then we have 4 of these in a larger cell, and again, 8 of these in a larger cell. So overall, you end up being 8 times 4 by 4 times 8. That would be 1,024 total elements. And then a lot of people ask me this question, so I'm going to preempt it, is that we use temperature to adjust things. How do you ensure the temperature remains constant? The way you do is that you have a lot of heaters and temperature controllers throughout the chip. So you don't let the system this side to heat up, then that side to cool down. You control the temperature very, very accurately. All right, so now you have a better camera, so you can see the structures better. This is that phase shifter again. I'm showing the same structure. This is a COMSOL simulation. This is a layout. This is the chip. This is a measurement. A lot of people asking about the speed, in that, okay, thermal effects are usually slow. Don't you need to have something that moves fast? So we measured it. All right, so we measured it. The fall and rise time was 50 microsecond. Now, you can say the 50 microsecond is too or fast, depending on your taste. But then, even if you don't like it, you can use electronics to enhance it. So we did it. So we can use something that's referred to electronics as pre-emphasis. And in doing so, you can just reduce it by a factor of 8. So you can get 5 microsecond of rise and fall time, which is good enough. When you're trying to laser steer the beam, you don't need to have gigahertz. Variable attenuator, we've seen that before. And then, obviously, there's a lot of electronics that goes into it. I'm not going to bore you with that, but you need to have electronics that especially not only control things, but also would compensate for the non-idealities of the optical components. So we did that. And then this time, the system was big enough that we needed to actually properly package it, and people needed to see it, so we had to give live demos here and there. So the chip sits in here. There is an optical fiber that is attached to this, and it goes out, and then the electronics control come out, go to a microcontroller to a PC. So when you measure, what you see in an IR camera is that the beam that can be steered, and if this is not clear enough, I'll show you later measurements. 1,000 elements was very scary. We were scared of the calibration. We didn't know how to calibrate it. So we first attempted a subsection, which was a 32 array. So we measured the 32 array, and after a lot of time on calibration, you can see that light can be steered in different directions. And it's very, very narrow. It's only 1 degree. And you can see Cartesian and polar plots. And then we attempted to measure the whole system, which is a giant system. Light comes into here, it gets divided. These are all divided into 1,000 paths, 1,000 phase shifters, et cetera, and they all add up into these antennas that are spaced by 1.2 lambda away from each other. This was also implemented in the Global Foundries 180 nanometer SOI process. And then after calibration, sure enough, you can form a beam, and the beam now is really, really narrow. So it's perfect, it's 0.03 degrees. So, yay, we're very happy. And then, of course, when you do research, you always have to brag about what you do compared to others. So you should show a figure, and you make sure that what you do is highlighted and what everybody else did bad is also highlighted. I'm not going to do that, though. I'm just showing you the facts. In fact, I am very, very pleased that since then there has been some very, very good work by other people too. In particular, just a month or two ago, Columbia, Lipson's group, they came up with some very good results also. I think we still have the largest number of elements with this performance, but again, there are very good stuff that's happening, and my students and postdocs are also very interested in the entrepreneurship aspects of this. Just Silicon Valley alone, I think there's been over $1 billion of investment in startup companies who work on car LiDARs. So people are interested. We'll see how it goes. In summary, optical phased arrays can enable a lot of different applications, 3D displays, imaging, holography, etc. There's a lot of research that remains to be seen. As I said, 2D phased arrays don't exist. All the phased arrays have been working in infrared. There is a lot of interest to work in the visible range. Nobody knows how to do that. We don't know how to calibrate these large-scale systems. And nobody has really created a system. Everything has been just a phased array. So I think the analogy I can give is that it seems that we're in the year 2004 when we were doing the RF. So this was like a first RF chip in 2004. So in 2018, we're about 10, 15 years behind the RF. So we still have a lot of catching up to do. So in the summary of this talk, I think phased array in general, or interference, is a very powerful concept that enables manipulation of the near and far field. Phased array concept is applied not only to electromagnetic waves, radio and optical, but also acoustic waves. If you've ever taken an ultrasound, or if you know a relative who has taken ultrasound, all of these ultrasound systems use acoustic arrays to try to find things inside your body, including the babies. So it's a very powerful concept that can be used in many different domains. And I think the monolithic realization of large-scale arrays, whether they're in RF domain, whether they're in optical domain or acoustic domain, continues to be an interesting research. I think I'm right about on time, but I'll leave some time for questions and answers.
That was perfect. Let's give Professor Hashemi a great hand.
Thank you.
That was really terrific.
Thank you.
Well, you led the way in millimeter wave phased arrays. You're leading us into optical phased arrays. Any questions for Professor Hashemi? That was quite a talk. No questions? There are a couple, yes? How much time do you dedicate to your research? And the students, how much time do they dedicate?
Very good. I'm assuming that your question is at the current moment, not in the past. Unfortunately, as a faculty member, you have a lot of responsibilities that are beyond you yourself going to the lab and conducting research. Most of the research is done by PhD students and postdocs. As a faculty, I get to meet all of my students on a weekly and daily basis, depending on whether they're senior or junior, try to help them with the ideas they have, try to sometimes give them ideas. If they have questions in the lab, go and try to solve it in the lab. But I also have to do a lot more than that. But the PhD student and postdocs are the real people that carry on the research, and they work day and night. I mean, I'm not exaggerating. I remember that when I was a PhD student at Caltech, we had a motto that was, sleeping is a luxury. We just don't sleep. And that was true. I remember that I would do a lot of all-nighters. I mean, I didn't even think about sleeping when I had a tape out. So these chips, for instance, when you're trying to fabricate a chip using a global foundries process, guess what? Global Foundries is $1 billion foundry. When they say, I need your design by 5 p.m. on a Friday, that means that they need it by 5 p.m. on a Friday, not 5:01, which means that it doesn't matter you're late or early. So if it comes to not sleeping for a month, you're just not sleeping for a month. So again, these things seem a little bit of exaggerated nature, but if you come to my lab, despite my persistence, they should not be the case. You find sleeping bags in the labs, in the offices. So there's students work a lot and postdocs work a lot. But I'll tell you something. Nothing compared to the pleasure that it comes into things actually working. So yes, there is a lot of work, but it's all by choice. In fact, being in Southern California, I always tell my students that if you don't like what you're doing, you're stupid not to go to the beach. I mean, the beach is right there. Just go to Santa Monica and enjoy the beach. So we don't check on them, but I hope that gives you a picture of how things work. So usually the ideas come from me. I guide the students initially, but they really take it on and lead the way after.
And that's what you need to do to change the world. To change the world, to invent, to make these new things.
Yeah.
It's a tremendous amount of tenacity and commitment and passion. The students work day and night because they love it and they know they're first. They know they have a chance to change the world.
And as a faculty, we work very hard. I mean, you shouldn't ask me, you should really ask my wife, because to her, we don't have a life either. We mentally, we're constantly working. I think that I'm always looking at my emails. My students call me in the midnight, and she's like, why would they call you at the midnight? Let us sleep. You know, these things happen. But again, I think those are the real people behind the scene.
Thanks for the question. Another question?
Yeah, you said you're struggling to do 2D arrays. What prevents you from simply like layering the linear arrays you have now on top of each other in a single chip?
2D arrays for optics, the distance issue.
No, actually, you're asking this really good question. So I'll tell you this. So if you need to stack them, you also need to, not only, you cannot be on top of each other, they have to be also staggered this way, right? Because right now the light comes from the top. So one way you can do is exactly what you said. So imagine that you have a chip. If the light came from the side, then you can have a lot of them on top of each other, and then you can stack in two ways. And believe it or not, this is how current LiDARs work. So the way they work, the Velodyne, is that although they're mechanically moving, they don't have a single laser that rotates around. They had 64 lasers stacked vertically. Each of them looks at a tiny angle, and they all move together. So one way is to do that. The problem is that it doesn't seem that it's scalable to very large arrays. So the LiDAR, the car LiDAR example, as much as it's great because it has a real market need, it's kind of easy because on the elevation, you don't need to scan a lot. I mean, as a car, you don't need to see the birds on top of you, right? You only need to see 10 to 20 degrees. So having stacking is okay. But let's say you're a drone, you're looking down. Now you need to see full 360 degrees in all directions, right? That solution may or may not be. But that's a very clever observation you had.
Thank you very much. On behalf of the ECE department and the NYU Wireless Industrial affiliates who support the seminar series in the lab, we'd like to give you a presentation, a token of our appreciation.
Oh, thank
Ivan
you.
Selesnik, the department chair, will come. Here, stand in the middle here.
Thank you very
Hossein.
much. Truly appreciate it. Thank you.
To commemorate this talk, thank you for coming to NYU.
Thank you.
And for such an inspiring lecture. And
Oh,
congratulations
wow. So
on what
lovely.
you've done. Let's give a hand for Professor Hossein Hashemi.
Thank you very much. Truly appreciate it.